Hi folks, this is your Professor Kent Schwickus again talking about our current chapter where we're going to be discussing gravity. Now, gravity is one of the four forces in the universe that we know about. There is speculation sometimes about a fifth force, which is sometimes used to deal with what's going on with the rotation rate of galaxies and why galaxies are connected together. That is something more for later lectures, talking about the Big Bang, or also in the Stars and Galaxies version of this class. Here we're just going to be talking about gravity, and for those of you that are already experienced with the knowledge of the four forces, you can also say that gravity is really not a force at all. It behaves quite differently than the other three forces that I've indicated here, and as such cannot be considered as a force. Anyway, we'll treat it as a force. It works pretty well that way. And remember, in physics, we're trying to understand how nature works, trying to understand how to be predictive in our modeling of it. And so the idea that gravity is a force works pretty well. The next thing we want to talk about is the fact that, there we go, that we do have these four forces, and I indicated before to you what they were. Namely, we have the electromagnetism, we have the strong and the weak nuclear forces. We're going to be talking about the strong and the weak nuclear forces when we talk about the sun, because they're deeply connected with what's going on with the sun. And electromagnetism we're going to be talking about next week. Electromagnetism, in a nutshell, is basically those forces that allow us to see. And most of the senses that we have around us are connected with seeing, some sort of electromagnetic connection between things. So your sight, smell, chemistry, taste, therefore, all have to do with electromagnetism. Gravity, on the other hand, is quite different. Gravity has to deal with the idea of masses, and because it's associated with mass, it can be considered as one of the strongest forces in the universe. On the other hand, electromagnetism at the scale that is associated with us, gravity is really pretty weak. You have to have a lot of mass in order to cause something to move gravitationally. Like, you cannot hold your hand over a ball and cause it to levitate, but you can hold the ball and cause it to fall to the ground because the Earth is pulling on it with so much mass. And that is with the difference at the large scales. That's what happens at the large scales. There's so much mass involved, and there's no way that you can screen the mass. And I'll talk about what I mean by screening a little bit. That all the mass comes and bears into the creation of motion. Now, what do I mean by screening? As you might know about electromagnetism, if I have two charges and they're opposite, one's positive, one's negative, then they will be attracted to each other. So much so that they could touch each other. Now, in the idea of atomic physics, those charges, if they happen to touch each other, would not annihilate each other. We're not talking about antimatter here. But they would come so close together that if you viewed them from far away, that you would not see any charge at all. That's what I mean by screening. On the other hand, if those two particles that had charge had mass associated with them as well, you would still see some gravitational force when you are far away from them. And the effect of the distance from you and those pieces of matter come into play. So, when we're talking about forces, we're going to be coming off of what we talked about last time, Newton's laws, and here you see the proverbial picture of Newton underneath the apple tree. Presumably you see the apple down here that he has just gotten bonked on the head from, or he can just be, you can think about him just contemplating it. And by the way, this tree still exists, or actually pieces of it still exist in England, and you can look it up and find out where you have to go in order to see it. But what we're interested here in this class is this equation, and I did promise you that we're not going to be talking a lot about equations, but it's easier and more compact to talk about it this way. And I talked to you before about how this equation is turned around. It really is, we want to know what the acceleration is on a particle, how it's going to change its position as a function of time, and predict where it's going to be. And so the forces of nature are embedded in this big F here, and gravity is one of these forces that belongs in there, along with the other three that I talked to just moments ago: electromagnetism, the strong and the weak nuclear forces. But we want to talk about gravity in this particular instance. So here is the universal law of gravity. It's universal because Newton figured out that it applies not only for those items on the Earth, like the apple, but it governs how things move everywhere that we can see. And in particular, in his instance, he was looking at what Kepler had discovered before, and Galileo before as well, that there is movement in the cosmos, and that movement is dependent upon this equation here. This force goes into Kepler's rules and describes why it works, or how it works, rather. All right, so let's talk about the equation. This is the F. This is the nominal force that we're talking about that's going to cause the mass to be accelerated in the previous chart. And it behaves in this following way. We have a constant here, G. We call it big G for short. It is a constant and can be measured, and it has this value. And a little bit later I'm going to show you how you would run an experiment like this in order to find out what big G is. Now, the force is also dependent upon how much mass you've got between the two objects that are going to be gravitationally connected. Okay, now remember Newton's third law, which we discussed last time, which is essentially, I can't touch you without you touching me. That's the nature of the force there, that third law. And so if we have a force between two objects, then those two objects are going to come into play by the masses of those objects. So we're going to have two objects, we're going to have the mass of one object, and we're going to have the mass of the second object. Now, the force also depends upon how close or how far away we are. Now, if you get far away, then the force goes down. If you get closer together, the force goes up. And in fact, it behaves according to a rule that as I go further away, then the force decreases by a square. Basically, I have to multiply the number by itself twice. So, if I increase the distance between these two objects by a factor of 2, then the force between them goes down by a factor of 4. Okay, so that's how we play the game. If the distance goes down by a factor of 3, then the force goes down by a factor of 9. Now, a little bit later, I'm going to be talking about how we really don't know G as well as we could. Now, this is the number that we have for G, and right now it is controversial, but it's controversial because we really don't understand what our experiments are telling us. We claim our experiments are known to 20 parts per million. I think that's like on the order of 1 drop of water in a swimming pool. Unfortunately, if I look at the various different values of G as measured by these experiments, the variation is on the order of 100 times larger. So in truth, we really don't know everything we want to know, but we do know this number to at least 200 parts per million. All right, so what I want to do now is show you that that if I have an equation that looks like this, and this is going to generate a motion on a particle, and that motion on that particle is going to be essentially, and I realize I'm saying it rather than showing it to you, it's going to be m times a, then the acceleration associated with gravity is going to be constant. It's going to be the mass of the other object times the gravitational constant times the distance squared. And so I'm going to show you that in a couple of ways. The first one is this video, and basically it's done at atmospheric pressure and vacuum on the Earth. Now it happens very quickly. So quickly you may not have seen it the first time. So I'll replay it once, and I want you to notice first, in the first case, when we had the air going, that the feather takes a little bit longer to hit the, quote, ground than does the ball bearing. And then when it's in the vacuum, they go together. Basically, it's occurring so quickly that you really can't see them float down together. You sort of had to view it, not focused on it, but get the whole picture. Okay, now this one is associated with NASA, and here, because gravity is so much less powerful on the moon, because there's about 10% of the mass of moon is about 10% of the mass as Earth, then the acceleration of gravity is going to be less. Naturally, you don't have any atmosphere here, and so the feather and the hammer are going to be dropping together, and they will actually be looking like they're floating down together.
Jim, we copied both solar wind and penetrometer drum in the ETD.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. Oh, I'll watch this. I have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
I think that's pretty neat, too.
Mr. Galileo was correct in his findings.
Now, when they reference Galileo, they're actually talking about Galileo's measurements not dropping cannonballs of various types off of the Leaning Tower of Pisa. That's apocryphal. but they were talking more in terms of his measurements of watching items go down inclined planes. Okay, now what I want you to practice at home are these demos that I would do in a face-to-face class. Excuse me, there are several of them. Basically, you get a book and a sheet of paper. You might need a couple of sheets because you're going to crumple up one. And you would want to drop them. And once the first one, I do this in a variety of different ways to get my students paying attention. But if you're going to be doing this, all you need to do is do it 3 times. The first one is you drop the book and the sheet of paper at the same height, at the same time, and you watch them as they flutter down. Now, naturally, the piece of paper is going to take longer to flutter down than the book. And the question for you is why? Now, most people would immediately jump to the conclusion that since the book is so much heavier than the piece of paper, then the weight of the book matters. But you've just seen in the preceding videos that the falcon feather and the hammer dropped at the same rate on the moon and on the Earth. If you're more accomplished, then you would say that it's air resistance that plays a role. And yes, air resistance does play a role. And the next experiment I would ask you to do is to lay the sheet of paper on top of the book and ask yourself the same question. Will they arrive at the ground, quote unquote, together, or will the piece of paper flutter up? And I would ask you to do that experiment. And you might be surprised. And then finally, I would ask you to crumple up the piece of paper and then drop it next to the book and see what happens. There are a number of variations you can do with this. You can have a number of loose pieces of paper and ask yourself, how long does it take, or how many pieces of paper do I need in order for the bundle of paper and the book to land at the same time? Or you can alter the paper axis and then drop the book and the paper at the same time. You can learn a lot about gravity by just a book and a piece of paper. These things will cause you, hopefully, to think about modeling the world around you in a better way. It just isn't the mass that matters here. Now, gravity gets smaller, as I said, as you go further away. And when you're here on the Earth, the gravity drops at a certain rate. It takes a certain amount of time. And if I go further out to here, this is twice the radius of the Earth, then it's going to take 4 times longer for the gravity, for that movement to be caused. And then out here, if I go out to 3D, then it's going to be 1/9, nearly 1/10, and then over here it's going to be 1/16, and then 1/25. So as I go further and further away, then the force gets less. This has to do with the fact that I can enclose the force causing mass here by a sphere, and that sphere basically governs the geometry of what's going on here. So that's why I have a 1/r², or 1/distance squared behavior of the force. So you can consider it's just a matter of geometry. And it's kind of interesting. Electricity and magnetism works that way, as well as the nuclear forces, although nuclear forces have other factors in there as well. Now, if we want to measure the gravitational force, this is the type of experiment we would do. We would have a torsional balance here. So we'd have a wire hanging from the top surface here and then holding a barbell with two masses on either side here. And then we'd put two big masses here. Now, if gravity is a force, then what we should expect is this wire is going to be twisted because there's going to be an attractive force between these two masses and these two masses. And we have it on either side like this so it's balanced. And this will cause this dumbbell here to move towards these two things here. Now, this is a very difficult experiment to do because the forces are here really, really small. If you recall in the very beginning, we have the entire mass of the Earth pulling down on your body, and that force, when we look at a scale, is somewhere in the neighborhood of 100 pounds. Now, me, I'm twice that, but that's because I'm so massive. I am putting on something around the middle. But a couple days ago, I did a 10-mile hike at 10,000 feet of elevation, and we came back, and it took us a little bit more than 3 hours to do it. So I'm still in relatively good shape, but the idea being is that the entire mass of the Earth pulling on me or pulling on you only creates about 100 or 200 pounds of force. That's like really small potatoes. Now, if it was electricity, you couldn't keep us apart. Okay, so this is the experiment you would do. And all right, now what I want you to do is we're going to show you a video of this Cavendish experiment that is being conducted. And I'll talk a little bit more about that afterwards.